someone has to do the night duty. So
We
often
don't have that problem, Taswald.
Exactly.
Yeah.
Maybe it's telling you that we're in the right country. I don't know what it's saying.
Yeah, you're in the European African zone. You're good. Julio's forever getting up at 5 and 6 a.m. and I'm forever working till 10 p.m. Guys in the middle of dominate.
You have a good excuse to have a late beer.
Yeah.
In your absence, I was just showing Taswald to guess what is in here, and I said it's not what Malcolm drinks.
Tea with lemon, I'd say you've got. All right.
Yeah, that's absolutely correct.
But we didn't actually, have to admit, arrange who's going to introduce Taswald. I'm sure it's going to be Aubrey.
Yeah,
yes, I'll introduce him.
You can do the honors. So. We are recording, so when you are ready,
okay.
You can start.
Your speaker's on, Tulio.
Thank you very much. I would like to take this opportunity to welcome you to another of the GCC seminar series. This series has been going since 2020, so it is very mature and it has contributed quite a lot to developing people and knowledge in our industry. Today we have a pleasure of listening to Taswald Moodley, who is an engineer, a senior engineer at Mintech. Taswald has many trades. He works in the area of comminution. He works in the area of flotation. He also dabbles in the area of computational mechanics. So today we have a privilege of listening to the topic, minerals processing optimization through the lens of scale. And I can assure you there will be some DEM simulation because of just the phraseology of the title. Let us listen to Taswald. Thank you.
Okay. Thank you, Prof. Aubrey. And thank you to the GCC, for allowing me to present. It's an intimidating audience. So, yeah, I hope I'll meet your expectations. So today my talk will be on, as Prof. Aubrey alluded to, minerals processing optimization through the lens of scale. Let me just turn my camera off because it's going to be weird. I've got the camera on the right screen. You might see me looking like this the whole time. Okay. Yeah. So you'll notice the first thing about my slide. I think the first thing is GCC guys. We need a clearer logo. The only one I could get on the web on the internet was this blurry one, but I think we need the graphics team to give us a much more high resolution logo. Secondly, you'll notice that there's a lot of. Just switch to pointer mode. Yeah. So you'll notice there's a lot of icons here on the screen. I work at Mintech. I've got an honorary appointment at UKZN, so I use some of the computational facilities there. We have partnership agreements with Ansys Rocky who enable us to do the DEM that Prof. Aubrey was speaking about. And of course, I'm a member of the Particle Technology Group, which is headed by Prof. Indressen. So many of the ideas here are seeded by his thinking and I'm just doing. So I'd like to just thank him and thank the rest of the team from all of these organizations. Okay, so the challenge, why scale matters. Plant models, there's two paradigms here. So there's a plant scale and the particle scale. And each have their pros and cons. And if we just look at plant models, they are often black box. So we can tell you what happened, but we can't probably tell you why. And on the particle scale, you get rich information, but the detailed simulations are too slow for daily use. And so performance emerges from interactions across the scales. Yet our models rarely link them effectively. And so today I'm not going to explicitly show how we link it, but it's more of a thought exercise to say, okay, these are the two paradigms of the research that I'm involved in, and maybe open it up to the audience to say, how do you best think we can link the two? So, okay, I've categorized modeling into two approaches, the top-down and the bottom-up. This is after seeing a colleague's presentation at Mintech. And so from the top-down approach, it's more of the plant scale approach. We predict the system behavior from measurements, and this is often done without resolving, and there's no need to resolve the underlying physics. So we have the data and we fit a model to it. So it works operationally, but it can be blind in some cases. In other words, it has limited diagnostic power. So to illustrate the point, if you consider this square box here, you start from the plant data, and that's driven by data availability. Obviously, you need a lot of data for this. And then you can do some mass balancing, you can enforce some constraints, and maybe you can fit a model to data. On the plus side, you get you can handle uncertainty. So you can say what are the bounds for the information that you have. And also, ultimately, what does it yield? It yields reconciled estimates of performance. And so in summary, as I alluded to before, it tells us what is happening. So on the other end, you have the bottom-up approach. This is when you're predicting behavior by explicitly modeling the governing mechanisms at micro scale, the small scales. And often it explains the physics, but it's impractical. It's not directly usable at plant scale. And to this point, even if you are able to model a specific unit, what ends up happening is that you struggle to stitch the units together. So here we start from the bottom. If you look at the green arrow, start from here. We start with the particle physics or the mineralogy, and then we build up and we say, okay, look, we can do some fundamental modeling, maybe simulation, or we can do some fundamental experiments, PEPT. We coarse grain it, or we take averages at meso scale, and hopefully we can produce reduced order models for scaling plant equipment. And so in essence, this bottom-up approach tells us why it's happening. And yeah, I've listed some points of advantages of each approach. So no one is wrong or right. And today, I guess the theme of the talk would be to say, give you guys examples of each approach and how I see or what you can do with obtaining a desirable result using each approach. Okay. So let's start with the first one, which is the top-down approach. And you see, I've got some pictures here of the pilot plant at Mintech. We have facilities to be able to run continuously, I think up to 1 ton per hour. And these are some flotation cells here, and we have our lab mills. And we do a lot of activities in scale up. Like we always try to go from the lab scale to the continuous scale. So you'll notice there's a trust handshake there. So we trust that we'll be able to do that. And let's look at example 1, which is typical of what we do with the data. So we look at a simple situation of just given a dummy example of some mass balance smoothing, which is typically done when we run plants at continuous scale. And in the first top-down approach, I know most of you are familiar with this, but for those of you that aren't, the algorithm for mass balancing involves us removing one of the variables. In other words, if you write down nodal balances at each point in our circuit, which is a dummy circuit in this case, you can remove the variable, in this case C, by assuming a concentration ratio. And then you can put it in matrix form and use a program like, in this case, Microsoft Excel, to solve for the variables unknowns. In this case, are your tails and your concentrate flows. I want to draw you to something. You'll notice that how you know whether you're in the right track or on the right track is you'll notice that before we solve, we have an error between measured and calculated flows of about 4.43. And after we solve, we get a lower error. That's typically what happens. Then we go on to plot our smooth flows against measured flows, and we hope that all of them lie on this parity line. Unfortunately, in this case, you can see that the underlying assumption of a steady state process does not capture examples when you have unsteady state performance at scale. And so that comes across even when you try to resolve it using this standard approach. You'll notice that if you change your guess values, I've solved with these green guess values, and you see that sometimes it diverges, and if you guess correctly, it can converge to a lower number. In other words, it depends a lot on your guesses. Gradient-based solvers, they may not converge, and it can't necessarily skip values once it diverges. And I think the worst part is that even if it converges, it's not necessarily a global minimum. It's sometimes local, like in this case, it converges to 3.1 to 2.2. And so in this first example, we addressed this issue by changing the game a bit. So what we did was we instituted a different type of algorithm that doesn't rely on the gradient-based solving approach. We looked at recasting the problem as a convex optimization problem where we invoke uncertainty. And how we do that is we change our objective function to be a combination of the AX equals B, which is the mass balance continuity that you would see in the matrix approach. And we also put some leverage onto the measured data. And so our new objective function is F1, which can be, let's say, this measured data plus some delta times F2, which is the mass balance continuity. And what this enables us to do is, this enables us to simulate all scenarios by varying this delta. And delta you can think of as confidence. Confidence in either you have low confidence in your measured values, or you have low confidence in your, or you want to put more confidence into your measured values, so to speak. And what this yields to us is it yields a nice Pareto distribution. And notice that all solutions that lie on this Pareto line are equivalent. The key point is that you can select solutions, in this case, within this purple box, depending on how confident you are in your measured values or how less confident you are in your measured values. And ultimately, the key takeaway from this whole exercise is that you end up getting a flow rate plus minus an uncertainty. It's a naturally emergent thing where if you look at all of these points and you plot them, you'll get a parity chart for each point. And in other words, it gives you some sense of the uncertainty in this case in your flow rate. And if you want to take your analysis to the next level, one can conduct a principal component analysis, which is also a form of reduced order modeling, if you will, where you can look at the relationships between streams. So you can look at all the tailing streams, which I have colored in blue. Yeah, I'm a bit colorblind. I think I used different blue here, different shades of blue. And the concentrate streams in red. And so what you can do then is you can account for the variances, meaning which components account for the most variance in your system, and you can use them to conduct a reduced order version or reduced order model. In this case, if we plot principal component 1 against principal component 2, we notice that there's different quadrants and there's clusters that form, like here the concentrate streams are forming a cluster, here C2 and T1 are forming a cluster. So you get some idea of which streams are grouped, and sometimes they're not too intuitive, you know. But the key point is that when they form close clusters, then it means that you can replace one of those streams by a linear combination of the other. So in this case, you can replace stream C2 as K times T1. And how that helps you is, it helps you because these principal components can be thought of as a dimensionless number that represents the system. And if you want to achieve performance or keep performance at larger scale, the game now is no longer to look at optimizing the entire mass balance, but it can be reduced to optimizing just these two principal components, which of course have been reduced, where when we see clusters, we've even reduced those streams, or we've taken those streams as linear combinations of the ones appearing near to them. And I guess this helps if you're trying to control your system from a process control perspective. So these will be the equations that are put into the PLC. So the takeaway from this first example of the top-down approach is that we can get a measure of the uncertainty in a flow rate. Moving on a bit to maybe a flotation example, still on top-down approaches. In this case, we're looking at selectivity. This is an LG sample, you know, with the way that UG2 ore is depleting, we have to start looking at other sources. And the reason why you may be wondering why I want to specifically talk about this example, it turns out that the selectivity criterion that's being used here has some roots in comminution. So here you look at your standard PGM recovery kinetics versus your chrome kinetics, and those of you in the flotation industry will know that you get penalized based on the chrome recovery, and in many cases you want to limit the amount of chrome that you recover per gram per ton of PGMs. And so here I've just shown the traditional calcil model that's fitted to grade and recovery versus time data. But Prof. Furstenau, whom I first read about in the comminution field, came up with this nice Furstenau selectivity curve combining the recovery kinetics of chrome and PGMs, and he created an objective measure of how selective you are. So you'll see that it compares the PGM recovery to the chrome recovery, and it says that if you above this parity line, then you're doing good. So I think that this is a nice objective way of determining whether you're performing well, particularly in a quote unquote top-down approach. So taking things further, you'll notice that I previously showed you some recovery kinetics. What we've been delving in is how can we extend this recovery kinetics to a mineral basis? And so this work that we did in for copper sample is now looking at how can one incorporate mineralogy information like liberation information, the modal concentrations of the minerals, and in essence get a recovery that is able to be constrained by the measured values of your total copper recoveries and the measured values in your feed modals and maybe your concentrate modals, but you get a kinetic curve based on each mineral. And so this is what you see here. This is for a copper ore, a sulfuric copper ore. You'll see that this curve here on where my pointer is the different concentrates, and each color or each bar represents the total recovery in that concentrate, but each separate color represents a different mineral, in this case bornite, chalcocite, and chalcopyrite. I've also put the residual copper that's recovered through non-true flotation. So the key point is that we constrain this by the measured data. So you see that the measured data points are the black circles, and our predicted recovery obviously is the sum of all of these individual recoveries, which is the red triangles. And obviously we have an error bar based on the uncertainty in our measurement. You'll notice that our model for based on a mineral by mineral species nicely sits within the error bars of the measured value. So we think that we're on the right track in this case. And this graph on the right-hand side shows you the individual mineral recoveries. I think just take note of the residual recovery. You'll notice that we've not we've allowed it to evolve naturally, and we've not constrained it to a typical calcil type of recovery, and that's on purpose because in many cases the residual recoveries consist of minerals that are hard to recover. But the big benefit of adopting this approach is that one can also look at the mechanisms of recovery. Like in this case, I've looked at true flotation, which is the shaded blue region, versus entrainment, which is a shaded gray region. And you can see the contributions of entrainment are low initially, but as you increase the time, you see that the entrainment becomes a dominant feature. And so using this approach, this is just to show that it really doesn't matter which CALSL model you assume, whether it's a 1-term, 2-term, or 3-term, all give you the similar information within a degree of error. But the takeaway messages from this is that at least we've been able to partition the copper recovery in terms of true flotation and entrainment. And we've used our mineralogical constraints to solve for mineral specific, in this case, bornite, chalcocite, and chalcopyrite. And the good part is we are able to recover the measured data. So you can see by the red triangle versus the black circle. The takeaway message from this slide is that this type of analysis yields a recovery and an uncertainty. Yeah. The previous analysis we did yielded a flow rate plus an uncertainty in the flow rate. Here we're yielding a recovery and an uncertainty in recovery. So the next question may be, you've shown us these top-down approaches. How do we use this information that we've got? So what I've done now is I've done a very bare bones economic or techno-economic analysis to present data that investors would care about. And I must state upfront that I've been watching a lot of GCC seminars, and the inspiration for doing this was taken from Rajiv Chandramohan's GCC presentation he gave last year, and also through my conversations with Prof. Andresen. And so these are some of the parameters that investors actually worry about. The net present value, meaning the value of money today, the return rate, how fast they're going to get their money back. And this is, the rate, it means the percentage, how many percent of their money they get each year back, and the payback period, how long it'll take them, and the risks, obviously. And so now, going back to the previous slide, we said that we have an uncertainty in recovery. And what we're trying to do is we're trying to translate that uncertainty in recovery into an uncertainty in revenue. And so revenue is given by this expression, which consists of various variables, and I'll just list the variables. I'll call them out in case you're wondering. It's throughput Q, grade, feed grade, availability, selling price, and cost of, or selling costs, if you will. And so in the first instance, I've taken these as fixed costs, and the only variable is my recovery. Like I've taken an example, 82 plus minus 5%. When you plug in the numbers, you notice that the downside is 365 million per year, the calculated downside, meaning if you take a 77. So when I say downside, upside is the best case scenario, which is 87%, 82 plus 5. Downside is the worst case scenario, 82 minus 5. And so we notice that even in the downside, every 1% change of recovery, it moves the annual revenue by this amount. Notice in the first example, I've taken recovery as the only variable. So how do we propagate this into cash flows? Well, your cash flow is given by your revenue minus your OPEX. And I've taken OPEX as a fixed cost in this first case, which is not, but anyway, for simplicity. And then you can calculate the downside. But more importantly, you can approximate the net present value using this expression. An important component of this expression is this R, which is the discount rate. The relationship between net present value and the R can be given if you take the derivative of the net present value. You can notice that if you take the derivative of the net present value with respect to R, you get this expression. And when you examine this expression, you'll notice that when R is less than an IRR, which is a special discount rate, then your net present value is greater than 0. The IRR in this case is just when the net present value is equal to 0. But I've just assumed a 10% discount rate in this case, and I've just given you the 3 scenarios. So we have our downside, meaning the worst case scenario, our base, which is if we achieve the 82 on its own, and the upside. And I've listed all our net present values, our internal rate of recovery, percentages, and how long investors will take to get back their money. So in this case, in this very simplified example, using the information from my Kelso curve in copper before, at least we have something telling us about the financial risk and upside. And if you're an investor, it says that your net present value is always positive, which is a win, you know? Yeah, I've taken a 5-year period, and it says in the worst case, it'll take 3.5 years for you to get back your money. But this project in a nutshell is value positive. But the problem with this analysis is that I haven't incorporated the probability of success. So I've only listed that this is what happens at this scenario. I've given 3 scenarios. So if you want to take it to the next level and account for the probability of success, then we have to do some probabilistic modeling. So we invoke some Monte Carlo modeling, and we say that the recovery will be about some mean and some standard deviation. We obviously have to bound it because there's some cases where even when it's random, it can select outside. The key thing here in the Monte Carlo simulations is that it's highly dependent on the variables it's highly dependent on the distributions that you choose for your variables. So in my first case, I'm only using recovery as a variable, and I've assumed that the recovery, even though it has a mean of 0.82 and a standard deviation of 0.05, I've assumed that it's a normal distribution. I'll get to that later and why that's a restriction, but yeah, you go ahead and do the same calculation as before, but now you're doing it for random points, and you'll notice that the cash flow changes, you'll notice that your NPV changes and your IRR changes. So if you extend this for 10,000 points, you obtain this. So the purple box on the, this is my pointer now. Sorry, pointer froze. Okay, so the purple box shows you what happens if you only consider recovery as a variable. Oh, there I'm back. Okay, and sorry, the slide is just slow. Yeah, so it tells you what happens if you just consider recovery as a variable. I think the key point is that the solid red line is when your NPV is equal to 0, meaning that's your internal rate of recovery. And so in this case, it's the red line is your worst case scenario. The yellow line is if you achieve your 82%, and the purple line is your best case scenario. All the error bars, all the bars are greater than this red solid line. It means that you have a high probability of your NPV being greater than 0. In this case, it's 99%. If you take the area of the bars to the right-hand side of this red line, but divided by, the area of those bars divided by the total. And so in scenario 1, you notice that your NPV looks good and your IRR looks good. In this case, investors don't consider the discount rate. They look at the risk associated with that discount rate. They don't only want you to give them their money back at 10%. They say, no, there's 5% risk additional. We want the minimum IRR, the probability that it's greater than, in this case, 15%. So if you look at the probability that it's greater than 15%, meaning the bars above this red dotted line, you will see that it's 90% of the bars lie above them. So there's a high probability that you'll be successful. And in terms of money, your NPV will range from 90 million to 323 million. It's positive. There is a problem with this analysis, though. We haven't considered other variables. And earlier I mentioned that I only considered the recovery. But now what happens when we look at realistic uncertainties? So let's look at the price of the commodity, the grade, the throughput fluctuation. I've shown you in the first top-down example, we can get throughput uncertainty and operating costs. What happens? So I've just taken some arbitrary values there for these parameters. And now you'll notice, I think the key thing is to notice that before the red line was here, and even in your worst case scenario, you were still to the right of the red line. Unfortunately, now the red line is here, and now in your worst case scenario, you're making a loss. So that means that the probability of your NPV being greater than 0 is 85% only, whereas before it was 99%. Your probability that your IRR meets the investor acceptable margin of 15% has dropped now to 71%, whereas before it was 90%. your net present value, which is your profitability, if you will, your value of money today, and it's minus 40 million in the worst case scenario because it's to the left hand side of this red solid line, and in the best case it's grown to 470 million. So it's, you know, the analogy of Monte Carlo is all about gambling. So I guess what this analysis tells you is that the more risk you're willing to take, the bigger your reward. Whereas now you're sitting at up to 470 million. Before you were only restricted to 323 million. To end this particular top-down analysis, I must just state some limitations about what I've done here. A lot of these variables I've in essence just taken arbitrary uncertainties, and even the distributions they follow. Some follow triangular distributions, some follow uniform distributions. You'd need more data in order to get a handle from that. And so each scenario here, you will need information from different people, meaning each variable you can get the information from different people. Like let's say, for example, you need to know what is the uncertainty in recovery. You can look at the geologists. You can look at the mining engineers for the uncertainty in production. You can look at the process engineers for the uncertainty in plant recovery and OPEX. You can speak to the legal teams and the environmental guys for taxes and royalties, and speak to the guys from market analysis for commodity prices. Okay, so that brings to an end what is really possible in the top-down approach. So let's look at the bottom-up. Yes, yeah. Okay. So in the bottom-up approach, we're really trying to use fundamental data to answer the behavior that we see emergent at scale. And so in this case, I've just given 3 different examples. You see that this is the tumbling mills. This is a granulation process. Here you see avalanches. In essence, what's happening here is that the behavior, the macroscopic behavior of individual grains can either work for you, where it does something positive, like you can do granulation with it, or it can work against you. In this case, it can create avalanches, which is a risk to human life. So it's important to try and understand that from a fundamental perspective. Interestingly, the underlying physics of these processes are very similar. You know, they consist of similar forces, but they might be in different ratios. So in this case, it'll be the inertia of the grains, the viscous forces between the grains, and maybe pressure coupling, if you will. And so this bottom-up approach consists of us doing experiments and maybe simulations using fundamental approaches. So let's talk about our measurements that we do. In this case, we do these positron emission particle tracking experiments where we label a radionuclide and we embed this into a particle of choice within your bed, and you track this particle for a long time. And if you track it for a long enough time, then the behavior of the particle is the ensemble behavior, meaning the behavior of the bed. In this particular example, I'll be showing you a 460 millimeter drum. So someone in the audience will be thinking, oh, that's a big limitation because in industry, we don't get that size. And that's exactly the point. When you try to do these fundamental approaches, you notice that you struggle to scale up to industry. But we'll address how some workarounds for that. And in this case, I'm using a 50% volume filling of glass beads. And I'm making a very simplified water glycerol mixture made up to these different viscosities. And you see we investigating the effect of speed. Modeling approaches, as Prof. Aubrey spoke about. Yeah, this is DEM. You know, I've done a bit of DEM as well. Yeah, you just model the particles as springs. You'll notice that with the fundamental approaches, we have to make very big assumptions. So yeah, we assume that it's a spring and there's a dashpot which can release energy, which is responsible for energy release to prevent purely elastic collisions. In terms of modeling wet systems, there's a couple of approaches that we look at. We can either model it as a liquid bridge, where this factor h controls the bridge. When the particles exceed this distance h, then the bridge collapses, meaning the force between the particles. And we separate the forces into capillary and viscous. And the last approach is we can use smooth particle hydrodynamics. And all that is if I'm looking at the effect of what's happening at particle A, I can interpolate the effects from the surrounding particles. The benefit of using smooth particle hydrodynamics is that you're able to model free surface flows because the individual elements, they interact like similar to DEM particles, if you will. In terms of just an overall summary, when you do dry DEM, you can account for fluid effects, but implicitly, meaning if you tune your friction, you can account for fluid effects, and the complexity is very low. If you use DEM coupled with liquid bridge models, then you account for the fluid by these viscous bridges, if you will, and the complexity is still okay, it's medium. But if you want to do it using SPH, then you fully resolve the fluid phase. In fact, you are resolved for the forces due to acceleration, pressure. You resolve for a lot of the forces that I mentioned in the preceding slide, but the complexity is very high. So what do we do after we simulate? So in order to develop these continuum scale models, we bin our data using these voxels, if you will. You can see this is a rectangular voxel of L and length D. And so what we do is we take our system and we make a grid of these voxels in 3 dimensions, and we bin the information inside each voxel. And this picture that you see on the left-hand side after binning results in this 2D image here. So you'll see a lot of these 2D images as I go on, and this is the genesis of how they were obtained. You get a nice picture of the velocity field in this case. Interestingly, due to time constraints, I can't go into the types of binning algorithms that we do use, but they vary based on whether we're doing DEM data or our experimental, which is PEPT. Okay, and this is just some information of how long it takes to do simulations. You can see SPH DEM takes about a week. You can do about 4 million elements, and it only gives you 6 simulation seconds. That's another limitation of these bottom-up approaches. You're also limited in terms of, besides the size or the scale of the equipment, you're also limited as to how long you can measure information for. And we have some fairly fancy graphics cards, so you need expensive hardware to be able to complete these simulations. With the liquid bridge or the dry DEM, it's fairly short. It only takes an hour to get about the same number of simulation seconds. And also the benefit is you can do it on your CPU, if you will. So in order to get confidence in our data, we first have to compare whether we're able to recover our PEPT, which is our known experiment. As you can see here on the left-hand side, this is the DEM, and this is the PEPT, and this is the error, meaning the bin by bin error. Blue means low error, green means yellow means high error. So in this case, we have mainly low errors. I think here I've listed it for 16% error. When one considers the solids fraction, we get similar type of performance. We get low errors, blue everywhere. And so what this tells us is that now, at least our first test, which is just looking at the bin by bin coverage, we close to, we can have some confidence in our predictions. We can't stop there though. We have to look at other features in order to say that we can trust our simulation information fully. And so other things we look at is we look at the free surface. In this case, we fit streamlines and we follow the streamlines to get what the free surface should be. And we can compare that from DEM and PEPT. In this case, we have good comparison between DEM, which is the dotted line, and PEPT, which is the solid line. So we overlaid these streamlines onto our velocity field. Then we look at perpendicular slices through the bed. So if you take perpendicular slices through the bed, you can also compare the PEPT and DEM that way. And the last one is once you have the streamlines, you can look at the turning points of each streamline. You can fit an ellipse, and that's the basal surface. And so you can also compare the basal surface. So this is done so that we can use our simulated information. The simulation is really powerful because it gives you information that you can't measure. You can't measure pressure. You can't measure stress. It's the only way you can be confident that the information you get is true is if you compare the kinematic information at least to PEP. So in this case, we can say that we're fairly happy with the quality of the matches from PEP to DEM. And now we can use DEM to do interesting stuff. So one of the things that we do is we look at these rheologies or these relationships between or that govern granular flow. Now, one of the popular rheologies is the mu-I rheology, and I won't spend too much time, but it's just the relationship of two scales, a shearing scale and a plugging scale or pressure scale, if you will. Importantly is these dynamic information that you need to be able to test these rheologies. You have to get them straight from DEM. And because we have a good or confidence in our DEM information, we can now confidently investigate some of the behaviors. The nice part about this number is it's dimensionless, and it also tells you something about your system. Obviously, if the numerator is bigger, then it's a shear dominated flow. And if the denominator is bigger, then it's a pressure dominated flow. And so you can use that to construct the same 3D maps, 2D maps, and you'll notice that in the flowing layer, it's shear dominated. And in the rising layer, it's dark blue, it's pressure dominated. And so using this type of information, one can build these granular flow models or these mechanistic models that can be used to scale up equipment. So in conclusion, this is the last slide of this section. I've just given an example of what's possible if we adopt this approach and follow it all the way through. If you're looking at the velocity field for a 70% critical speed with three approaches. One is PEPT, which is the measurement. One is DEM, which I've just shown you. And the other one is the theory that's been developed within the particle technology group. If we compare these three approaches, well, firstly, you can see that the velocity fields match within a small degree of error. So at least it shows that the theory matches the PEPT and the DEM. So it's a tick, it's good. But if we use a different lens to evaluate what is the cost of each approach, what is the downsides, the pros, then I've just used these two categories to end with. The time to a solution. So once it's built, once the thing is built, how long it takes to give you an answer? Well, turns out that the time to a solution for theory is low. You can get the answer in seconds on a spreadsheet, if you will. Also, it's accessible by low-level staff, maybe an operator or someone that's not maybe trained specifically in that area. PEPT, on the other hand, the time to solution is really high. It can take in the order of months for you to get some type of an answer. DEM, on the other hand, it has a medium time to solution, so it takes in the order of weeks. But unfortunately, both PEPT and DEM, you need a high level of skill to be able to do them. So what are the cons? What's the barrier to entry? So the barrier to entry for the theory is high, and I've listed this. I've given the reason because it took Prof Andresen since 2020, maybe even before that, to now to develop this. So it's a high, fairly high. It requires a large level of expertise and many years in the field to be able to build it for combination speeds, if you will. The barrier to entry for PEPT, very high. Nuclear facilities, funding, accessibility, high degree of skill. Lastly, the barrier to entry for DEM, medium to high. It can take months in a PhD to be able to effectively or confidently be able to do some of these type of predictions. And so one can see that even within the fundamental approaches or the bottom-up approaches, there are some considerations that one has to allow for in terms of achieving one's goal. So in conclusion, you saw that from the top-down approaches, we got some robust financial estimates from the data. From the bottom-up, the simulations, DEM, and measurements, we can provide the mechanistic why. We can tell you, if you look at the inertial rheology, when is it pressure dominated, when is it shear dominated, and it can and importantly, it can predict beyond historical data. And this is an open question to the audience, or a statement, if you will. The two approaches are strongest when linked. Top-down supplies context, and the bottom-up supplies the insights. And so, how do we couple the two approaches? So, thank you for your time, and I think I'll hand over to the session chair.
Thank you very much, Taswald, for that wonderful presentation. Quite a lot of information there. Are there any questions for Taswald?
Well, I've always got a question. Yeah. Haven't got anyone.
Go for it.
So Taswald, the bottom up, and I liked your last example. Once you spent a decade developing the theory of the model, it can then have a quick use and be applied into industry. And I think that starts reflecting. Without that other insights, you don't get to that model. So I kind of looked at your row there, going from PEPT and DEM to building the theory based on granular flow. And I'd say that's a pathway to linking to the bottom down, because that's something that can be run in a online model. So I think your last point is really taken there. The others, there's such a distance between them, they're more difficult to link. But if you can get it into an analytic solution, that really seems to me to form the strong coupling for use.
Thank you. So that was a comment. Let's take another, and then Taswald can, maybe three, then Taswald can respond. Mohsen?
Hi, thanks, Aubrey, and thanks for the good presentation. One question that I had was actually when you did the economical analysis, especially when you had looking into NPV and IRR by changing those variables like grade and throughput and those factors. I was wondering if you managed to do some sensitivity analysis and whether you got some insight in terms of which of those values actually has a greater impact on NPV and IRR.
Thank you, Mohsen. Let's take one more, then we can give Taswald the floor to respond. Any other questions? Okay, Taswald, you can respond to the two, and then we'll move forward.
Okay. So the one I have a good response to, the second one is a work in progress. So, Prof. Malcolm, the building it up, getting the analytical solution, you get it up to one unit operation. And now you have to stitch those unit operations together. And it means that you have to rinse and repeat for each unit operation, and hope that you a lot of the assumptions that are made when developing the theory are really, really fundamental assumptions that may not necessarily capture emergent behavior. So what happens when you do plug it in with recycle streams? What happens when you do have to account for wear? These are all questions that I'm posing. It is excellent to get it into that analytical form, but I think that there's still development needed, even at scale. There's still calibration required moving up. Yes, the physics remains similar, but perhaps some of your assumptions that you made when you were considering it in isolation may not necessarily be so stiff at the large scale. I hope that I've understood your question and answered reasonably.
Yeah.
Okay.
Thank you very much, Taswald. Second one.
Okay, Prof. Moisen, I hope you're well. I haven't been to the JK since 2022. Yeah, to get to that point, you know, the real challenge for me was getting the data. So I had to thumb suck some numbers, you know, I had to thumb suck some of the standard deviations, because that's also largely controlled by the standard deviations that you use, or the amount, how much you allow each variable to fluctuate. Furthermore, what type of distribution does each variable follow? When you don't have data, maybe it's better to use. See, I got my alarm. It's reminding me my 45 minutes up. Yeah, sometimes when you don't have a lot of information, I think Prof. Andressen was just telling me that you might need to use a triangular distribution, maybe a uniform. If you have if you want to simulate, I mean, an interesting one, Prof. Moisen, is if you want to simulate what happens if there's an external influence into your plant, you simulate that by using a bimodal distribution. You know, you can't get a bimodal naturally. There's some external stimulus. And so to answer your question, Prof. Moisen, the reason why I haven't yet done the sensitivity analysis is because I want to get a handle on what are the deviations of each individual variable, and more importantly, what type of distribution does it follow. And I think once I have that, then I can confidently say that, okay, these are the drivers behind your system. So I'm just not in a place where I can confidently answer that question now. Come in, Moisen.
Yeah, just can I make a comment? I think I get your point in terms of not having access to all the data. My thinking was actually, if you just essentially trying to use the sensitivity analysis and change those parameters with a certain range, essentially the changes are arbitrary that you make. But what it does, it helps you to kind of narrow down the focus of your study to variables that has more impact on that MPV and IRR. Like, for instance, if you find, for instance, throughput, then even you change it by 20% plus minus 20% doesn't have a bigger impact comparing to ore grade, for instance, then you might actually put your effort to find more data around grade as opposed to throughput. So I'm thinking probably it's the best way to kind of filter some of these factors up front, and then put your effort to collect the data that actually is more impactful on your, essentially the bottom line.
So this is what Prof. Moisen is talking about. I've done that, but as I say, I'm just too scared to show it because I've dumped a lot of it.
Yes.
You know, what they say, always under promise and over deliver. I think that's the safer route. Guys, I think that allow Prof. Andressen to come in here. He's been looking at this in a much more detailed fashion than me. And so I think that he can maybe fill in the gaps where I'm weak. Prof, come in.
Thanks, Taz, and greetings to everyone. Yeah, so I think, Moisen, you raise a very important question. So of late at Mintech, we've been trying to think about how does one access funding through the lens of people that actually have money? And those tend to be the big investors. It tends not even to be our traditional sources of funding like government and so forth, but it's those investors that want to get into the new aspects of mining. So one of the things that we're looking at is trying to extract value from fly ash, and many people are talking about it. The scientific community and the environmental community is abuzz about all these activities, but the only people that want to invest in these are these investors, the sort of classic investors that look at distributions like these. You have to have an NPV distribution. You have to show that 70% of your NPV distribution lies above zero before they will even look at you. So when one does that, as Taswald alluded to, you have to do a sensitivity analysis in essentially the way that Moisen had pointed it out. And I've been doing this now in the space of fly ash. And I can just share with you that the big drivers are the usual suspects. It's revenue per ton, very, very important. So you need to be able to give huge confidence about that. Throughput capacity is second in line. OPEX per ton, you need to get that right from the get-go if you're going to realize your NPV values, which is your present day value at a future time. And it turns out that when you want to get into the risky stuff, like fly ash, you have to now design a plant for fly ash that essentially doesn't exist. Then the most important driver, or in the words that Moisen had used, the most sensitive, the highest sensitivity is actually the discount rate. So as researchers, if we're going to go to investment houses and ask them to invest of the order of billions of dollars, then those investment houses will specify the discount rate, and they will not be flexible on that. They will usually set that quite high. So I noticed Taz has used a very nice 10%, I think. But if you want to invest in something risky, that's going to be 30%. And from that 30% discount rate, which Taswald denoted as little r in his presentation, if you'll find that that exhibits the most sensitivity. So when you're doing the Monte Carlo simulations, what you have to do is allow the discount rate to vary as well, such that the family of all possibilities that could emerge in your distribution produces an NPV distribution that's still greater than 70% above zero. When you're able to do that, you can walk into the offices of these investors. If not, you just can't. The risk is too high for them to even talk to you. But I think what Taz is talking about here is it's opening a lens into accessing funding that I think us scientists, us technical people, just have no clue about. And so we knock on the usual doors of funding, which tends to give us very, very little funding. The actual rich people are not the mining houses. They're not the government. They're these rich investors that want to make a lot of money in these new ventures. So I think the lesson that we've learned is learning to talk their language becomes very, very useful.
Indresan, can I hand over the chair to you? I'm going to another meeting. So when you finish, can you please chair the rest of the session for me?
Ouch. All right. Guess I can.
Thank you. You volunteered. Thank you.
There are a few questions in the chat, perhaps, Andresa, and you have a look at those also.
Quinn, would you like to say something? I see that you put some comments in the thing. I think while Prof. Indresan looks at the comments.
Yeah, I think you've probably covered a lot of it in the discussion already, Taz. I think, yeah, one of the things I was just wondering about, I mean, you talked right at the end of your slide about linking up the top-down and the bottom-up approaches. I think there's quite a lot of work happening in the AI and ML spaces at the moment, looking at sort of things like physics-constrained models, where you essentially use your insights from the physics to constrain the training of your data-driven models, and that basically lets those models be a little bit more applicable broadly. So I think that's possibly one angle you guys can have a look at if you're not doing it already. Yeah, and then I was just sort of saying, yeah, I mean, I really enjoyed this whole presentation on the, how uncertainty propagates through your problems and things. And I just wanted to point out there is a whole actual formal field that does this called uncertainty quantification, where they look at the mathematical statistical propagation of uncertainty through these kinds of systems. So again, probably nice thing to have a look at. There's probably a lot of papers out there that would help you, even though they're not directly in our field.
Thanks very much, Quinn. Sorry, guys, I'm not really sure of the protocols here, but are there any other questions?
Yeah, don't worry. Maybe I can assume. Yeah, and it's
Yes, please, if you could. Thank you.
I can do it. Yeah, but if you have any further questions, maybe we can open for an additional one, and then. So if we don't have, I think we are running out of time, but let's thank Taswald again for the very nice presentation. And thank you all for attending this seminar now this month. So next month we'll have another one. Yep,
just before we go, Julio, I just want to check if Moisen is covered. Moisen, you didn't say anything after Prof. Andresen spoke. I'm just checking if you covered Prof. Moisen.
Yeah, no more comment. It was very good, I think.
Okay.
Thank you very much.
Okay.
And very well done. It was a very good presentation. I really enjoyed it.
Okay.
But thank you, Taswald. Thank you all for attending.
Thanks, Taswald. That was great.
Thank you.
Thank you, everyone, for joining us. Yes.
Thank you.